Real quick, before we start solving equations, let's read the directions that hold for this section, both in your book and in MyLab Math. The variable theta indicates the angle is measured in degrees, whereas x is going to indicate the angle is in radians. All decimal approximations should be given to 4 places after the decimal point. All right, so let's get started with linear trigonometric equations. So the first thing we need to do is talk about how you recognize that you're dealing with a linear trigonometric equation. The first bullet point says a linear trigonometric equation is an equation in which all the trigonometric functions involved are raised to the first power. Okay, so let me elaborate on that. If you have a trigonometric function, and what I mean by this phrase, I keep saying it, trigonometric functions, I'm talking sine, cosine, tangent, and so on, these guys. Okay, so if it's linear, every trig function that's involved is going to be raised to the first power. So what that means is you won't see things like cosine squared of x or tangent to the fourth of x. Okay, now you might wonder, well, what about cosine of 2x? Okay, something like that. That's a double angle because you have the 2x, but this piece is actually linear. Okay, so this is linear because the cosine is not squared. You don't see a squared on it. Okay, so that's what makes that linear. Okay, it's not, don't let the 2x confuse you in the double angle part. Okay, so what would be bad is something like this. Okay, where you're raising your trig function to a power. Okay, so I'll write here, these guys are not linear. Okay, all right, so one more time, if you've got a linear trigonometric equation, it's an equation. All of your trigonometric functions involved are raised to the first power. Okay, how do we solve a linear trigonometric equation? Well, there's a couple of ways. Okay, you could have a linear trigonometric function that contains a single trigonometric function, meaning your equation only has cosines, for example. Or you could have a linear trigonometric equation where it has more than one type of trig function. Okay, so the method you're going to use to solve your linear trigonometric equation depends on whether all of your trig functions are the same or if there's more than one type of trig function. Okay, so if you read the second bullet point here, it says to solve a linear trigonometric equation that contains a single trigonometric function. This would be the case like if you had all cosines. Okay, you're going to isolate the trigonometric function on one side of the equation. Okay, if instead you have an equation that has more than one type of trig function, you're going to use factoring. Okay, so let's try each of these methods out. Okay, in example 1, it says solve the equation over the interval 0 degrees to 360 degrees and also for all solutions. Okay, so the equation here is 3 times the tangent of theta minus the square root of 3 is equal to 0. Okay, so let me say a couple of things before we actually solve. Okay, first of all, notice the variable here is theta. Okay, that means that theta indicates that we're in degrees. Okay, if you don't remember that, okay, they're going to tell you in the directions. So you can see right here that the angles need to be in degrees for this particular problem. Okay, so we're coming up with basically a couple of solutions here. You first need to find all the values of theta between 0 degrees and 360 degrees. That's one revolution of the unit circle. You need to find all the solutions in one revolution of the unit circle. And then, like I said, we know that trig functions are cyclic. Okay, they repeat over and over again. So then you have to write a more general statement that you can use to find all the solutions if you had to. Okay, there's because of the repetition, there's infinitely many solutions, so you can't possibly jot them all down. You have to write them in a compact way. Okay, so we'll talk about how to do that. Okay, all right, let's first talk about why this equation is a linear trigonometric equation. Okay, when you have this on a quiz or an exam, everything's going to be mixed up. Okay, I'm not going to be there telling you that this is linear. You have to be able to recognize what type of equation you're dealing with. Okay, first of all, notice tangent of theta, that's our trig function, it's raised to the first power. Okay, I don't see a tangent squared or a tangent cubed. This guy is raised to the first power, okay, which makes it linear. And what's also nice is it's our only trig function. We don't have a secant involved. We don't have a cosecant or a cotangent. This is the only thing involved. Okay, so what we're going to do, if you have something linear and it's only got one trig function, you're going to isolate the trig piece. Okay, meaning what I just highlighted, this tangent of theta, I want to get it by itself on one side of the equation. Okay, so here we go. So I'm going to write it over here. Okay, I need to get this tangent of theta isolated. Okay, so first thing I'm going to do is I'm going to take this negative or this minus square root of 3 and I'm going to move it over. So I'm going to add the square root of 3 to both sides. Okay, so whatever you do to one side, you have to do to the other. Okay, so I'm just adding this to both sides. Okay, that's going to tell me that 3 times the tangent of theta is equal to positive square root of 3. Okay, I'm almost there. This tangent of theta is being multiplied by 3. So to undo that, I'm going to divide by 3. Got to do it to both sides. Okay, and then on the left, the 3's will cancel. We are going to get that the tangent of theta is equal to the square root of 3 over 3. Okay, all right. So the trigonometric piece has been isolated. Okay, what do you do now? Okay, well, we're looking for the values of theta. I need the angles that if I take their tangent, it's going to be the square root of 3 over 3. Okay, so we need to first find the solutions within one revolution of the unit circle. Okay, so you probably should look at your unit circle. So here we are. We need to solve this. Okay, what angles have a tangent of the square root of 3 over 3? Okay, well, this is a positive value. Tangent is positive in quadrant 1 and quadrant 3. Okay, so that's where we need to be looking. Okay, so which one of these angles is going to work for us? Okay, remember tangent is the y value divided by the x value. Okay, so I'll write that here. Okay, obviously these guys are not going to work, okay, because 0 divided by 1 is 0, 1 divided by 0 is undefined. If you do the square root of 2 over 2 divided by itself, that's going to give you a tangent of 1, so pi over 4 doesn't work. So it's one of these two angles. It's either pi over 6 or pi over 3. Okay, so if I just look right here and I do pi over 6, okay, and I figure out its tangent, the tangent of pi over 6 is going to be 1/2 over the square root of 3 over 2. Okay, so this is going to be 1/2 times 2 over the square root of 3. And so the 2's are going to cancel. I'm going to get 1 over the square root of 3. If I rationalize the denominator, boom, I get what I want. This is the square root of 3 over 3. Okay, so this is the angle that we're looking for. Okay, the tangent of pi over 6 is going to give me the square root of 3 over 3. Okay, nothing else works. I mean, if you wanted to, you could have checked the tangent of pi over 3. Okay, that would be the y value over the x value. So that would be the square root of 3 over 2 times 2 over 1. It would be the square root of 3. Okay, so that doesn't work. Okay, so pi over 6 works. Okay, but remember, you need to check one entire time around the unit circle. Okay, does anything else work? Okay, and again, why am I not looking at quadrants 2 and 4? Well, because in quadrants 2 and 4, I'm going to get a negative tangent value, and that's not what I want. Okay, so I need to come down here and look at quadrant 3, okay, where the where the tangent values are going to be positive, okay? So what do you think is going to work here? Since pi over 6 worked in quadrant 1, well, it's probably going to be, you're looking for the same kind of ordered pair here, okay? So we need to look at negative square root of 3 over 2, negative 1/2. It's probably going to be this guy, okay? So let's make sure tangent of 7 pi over 6, okay? Take the y value, divide it by the x value. Negative divided by negative gives you positive, so this is going to be 1/2 times, flip the bottom fraction. Okay, 2's are going to cancel again, and this is going to fall out the same way that pi over 6 did. This is going to be 1 over the square root of 3. Rationalize the denominator, and you get a tangent of the square root of 3 over 3. Okay, so we've got our two angles within one revolution of the unit circle. Okay, remember the angles are pi over 6 and 7 pi over 6, but we're working in degrees here. Okay, so it's going to be 30 degrees and 210. Okay, so I'm going to go ahead and write these guys down. Okay, so theta is going to be 30 degrees. Okay, and 210 degrees. Okay, so these are my two solutions within this one revolution of the unit circle. So 30 degrees and 210 degrees. Okay, now comes the little more difficult part where you have to write down all solutions. Okay, because if you keep rotating, you can just find an angle that is coterminal with 30 degrees or coterminal with 210 degrees, and that too will be a solution to the equation. Okay, so there's infinitely many solutions because you can keep rotating forever, either in the clockwise direction or the counterclockwise direction. We need a compact way of writing down all of the solutions. Okay, so if you go back to page 1, that was that blue statement I was talking about. Okay, it says finding all the solutions can be accomplished by first finding solutions over an interval whose length equals the period of the function, okay, and then adding multiples of that period to the solutions found. Okay, so we have been working with tangent. Okay, the period of tangent is pi. Whoops, period of tangent is pi. Okay, so what we actually needed to do, even though we were asked to find the solutions between 0 and 360 degrees, which is one time around the unit circle, the period of tangent is just pi. So you really only need to look at pi radians here, okay, when you're writing down the general solution. Okay, so really within one period of tangent, okay, we looked within 2 periods of tangent, but if you only look within a single period of tangent, you get one solution, 30 degrees. Okay, so what you do is you take that 30 degrees. You could use 210 if you wanted to, but you don't have to take both is the point. It's not wrong if you do, but for tangent, you only have to look at within one period, which is half of a circle. Okay, so you're going to take one of the solutions and you're going to add integer multiples of the period. Okay, so I'm going to use n. N is an integer. And I'm going to multiply by the period. Okay, the period of tangent in degrees is 180 degrees. Okay, so this is how you would write down the general solution. Okay, let me put a box around it. Okay, and remember what we said the integers are. Okay, integers are this group of numbers. Okay, you've got the counting numbers. I cannot count. Okay, so we've got the counting numbers. You've got their negatives. And you've got 0. Okay, so that's what the n is going to represent, and I'll go through that in just a second. Okay, So let me box this and I'll show you how it works. Okay, so to get all the solutions, I picked a solution within one period of tangent, and now I'm adding integer multiples of the period of tangent. Okay, so watch, this is how it works. Okay, I'm going to come down here and I'll use a different color. Okay, start picking values for n. Okay, so if n is 0, okay, plug in 0 for n. You're going to get 30 degrees plus 0 times 180. Okay, that's going to give you 30 degrees. Okay, we know that's a solution. It's one of the ones we found on the unit circle. Okay, bump up your counting number here to 1. Okay, so this is going to be 30 degrees plus 1 times 180 degrees. Okay, this is going to be 30 degrees plus 180 degrees. Voila, that's 210. Okay, that was another solution within one revolution of the unit circle. Okay, I can find another solution by letting n be 2. Okay, so this is going to be 30 degrees plus 2 times 180 degrees. This is going to be 30 degrees plus 360 degrees. Okay, this is going to be 390 degrees. Okay, 390 degrees is coterminal with 30 degrees. Okay, so that's another solution. Okay, and you could keep plugging in positive integers. Okay, but you could also plug in negative integers. If n is -1, you're also going to get a solution. So 30 degrees plus -1 times 180 degrees. This is going to be 30 degrees minus 180 degrees. That's going to be -150 degrees. Okay, and you could keep doing this. Okay, by picking a different n value, you're going to get a solution. Okay, there's infinitely many integers. It's going to generate every single solution there is to this equation. Okay, so that is in a nutshell how you do this. Okay, now let me say one more thing. If you wanted to, okay, you could have also said, hold on, I don't know why I drew it here. I was trying to draw it towards this all solutions here. You could have also done this. Okay, so this is also correct. Okay, you could have done 30 degrees. Okay, so let me go back to the unit circle. 30 degrees and 210 degrees are not in the same location on the unit circle. Okay, anything coterminal with 30 degrees is going to be a solution. Anything coterminal with 210 is going to be a solution. So you could have made two different statements. Okay, you could have said, all right, if I take 30 degrees and add any integer multiple of 1 revolution, okay, this is going to catch everything coterminal with 30 degrees, but you would also need a second statement here where you take the 210 and add integer multiples of 1 revolution, or add integer multiples of a revolution. Okay, so then that second statement is going to catch everything coterminal with 210. Okay, but if you wrote the blue statement instead, okay, the 180, it catches everything, but you only need one statement here, okay, because it will also catch anything coterminal with 210. Okay, so if you use the blue statement, it's correct. If you use the two red statements, it's correct. Okay, all right, so that is what you can do to solve a linear trigonometric equation where there is a single trigonometric function. You need to isolate the trig term and then go from there.